Hi everyone, welcome back. So in this segment, we are continuing on solving examples involving integration by parts. We have already seen the formula, and we're going to see some of the unusual examples here. For example, how do you integrate arc sine of x, or also known as sine inverse of x, or sine inverse of y dy? So this is a little bit similar to the ln x example we did in the last segment, where it's a single function, it's not a product, and yet integration by parts still can be applied. So we really have only one choice here. We're going to let u be sine inverse of y, because we don't have to integrate it, right? I couldn't write it over here. And let dv be everything else, in this case dy. So the integral of dv is v, and the integral of 1 dy is going to be just y. The derivative of sine inverse of y, you may recall, is 1 over the square root of 1 minus y squared dy. And if you knew the integration of this, if you know the integral of this is that, then you also know the reverse operation, right? The derivative of sine inverse is 1 over the square root of 1 minus y squared. Okay, so applying the formula, I'm going to first do u times v. So that's y times sine inverse, or arc sine of y, minus the integral of v du, which will be y over the square root of 1 minus y squared dy. Okay, notice we went from a complete unknown, something we didn't know how to integrate, to something that we think we can integrate, right? The y over the square root of 1 minus y squared. We should be able to do it with which technique do you think? If you said use substitution, you are correct, because let u be 1 minus y squared. So then du is negative 2y dy. And we already see a y dy on the top, so we know this is going to work with u sub, right? So let me continue down over here. So from the line above, keep the first term as it is. And then minus, okay, so here I'm going to make that an integral in terms of u. So it's going to be the integral of y dy will be replaced by du over negative 2. So when you divide by negative 2, I'm going to put on the outside negative a half. And then the denominator becomes the square root of u, or u to the negative 1/2. So here, the two negatives give me a positive a half in the middle. So y times sine inverse of y plus a half. And let's also go ahead and integrate u to the negative a half while we're at it. So this will be u to the 1/2 over 1/2. So it'll be u to the 1/2 over 1/2, or times 2 over 1. Here the 2's cancel, and we have y times sine inverse of y plus the square root of u. And at that point, I can also add my c, and square root of u, since u is the same as 1 minus y squared. So we have, after the plus sign, we're going to have the square root of 1 minus y squared plus c. So u to the 1/2 has been replaced by the square root of 1 minus y squared. Okay, any questions? Please let me know in class or send me an email. So for now, one thing we've learned from this example is that we can integrate a single inverse trig function using integration by parts. Okay, we're going to do a few more mixed examples now, applying the same technique. Okay, let's go to the integral of x times e to the x over 2. Okay, so this is a bit of a review question. I want you to pause the video for a minute, see if you can figure out what is u, what is dv, and then we'll go over it together momentarily. Okay, so first thing I would check is that this is a question that cannot be done with simple u substitution. Like if I had e to the x squared and on the outside x dx, yeah, I could have done that with u sub, but not this one. So I'm going to have to use integration by parts here. What would be a good choice for u? For questions of this type, we typically said let u be the x quantity x to the power, right? And du will be the derivative of that, which is 1 dx, simply dx. The only exception to that we've seen so far is if your x to the power is coupled together with a natural log function, then we did the opposite substitution, right? We let u be the natural log and dv be the power of x. But for other questions like x times e to the x times sine x, for those, it's a good idea to let u be equal to x. Okay, so for dv, use everything else, e to the x over 2 dx. And how do we find v? So we need to anti-differentiate here to find v. Think about it. E to the x over 2 can be written as e to the 1 over 2 times x. And e to the constant times x, the antiderivative is e to the constant times x divided by the constant, right? So we're going to have to divide by 1/2, which is the same as multiplying by 2. So divide by 1/2, which I did, and that's the same as 2 times e to the x over 2. Okay, now we're ready to apply integration by parts formula, uv minus integral v du. Notice at the moment I'm not going to worry about the limits. I'm going to plug them in at the end. So u times v will be x times 2 e to the x over 2. Put the 2 up front. Minus integral of v du. So multiply this times that. V du. So minus 2 times the integral of e to the x over 2 dx. And you could pull the 2 out on the next step if you prefer. So once I pull the 2 out, I'm going to have an integral that looks like this. 2 times integral of x over 2 dx. And just like we did over there, right, to integrate that, it's going to be e to the x over 2 divided by 1 over 2, or 2 times e to the x over 2, right? So then that 2 times will be multiplied with this 2 over here. So you're going to end up having a minus 4 once you integrate that term. Okay, so the first piece, just bring it down exactly as it is. Second piece, we'll pull the 2 out, and then integral of e to the x over 2 was 2 e to the x over 2, and the two 2's got multiplied to give us the 4. Don't forget the negative in the middle. Now we're going to evaluate from 0 to 3. And for that, start plugging the upper limit first. You can have 6 e to the 3 over 2 minus 4 times e to the 3 over 2 minus, and after that I would open a parenthesis, plug in the 0. 2 times 0 is 0, so that first part is 0. So then you're going to have 0 minus, plug in a 0 here, e to the 0 is 1, you're going to have minus 4. And the 2 negatives gives you a plus 4. Notice you can also combine these two together. 6 e to the 3 halves minus 4 e to the 3 halves. That is 2 e to the 3 halves. And then don't forget you have a plus 4 at the end there. So that is our final answer for that question. So that was nothing new there really. It was a review type of problem. But the trick was trying to remember how to integrate something like e to the x over 2. We're going to try to integrate x squared times tangent inverse of x. So clearly we cannot do this with u substitution, because if you let u be x squared, du is x dx, and we don't have an x dx here. What we have is an arctangent x dx, and you cannot separate the x from arctangent, right? That would be silly. So we can't do that. We cannot use u substitution here. Therefore, we're going to try to use integration by parts. Here is the deal though. Which one should we use as u and which one should we use as dv? Now, you could go through the trial and error process. If you let u be x squared and dv be tangent inverse, you would have to integrate tangent inverse to go from dv to v. And that is not easy. That's going to require a lot of work. I don't expect anybody to have memorized that, right? And it gets more complicated. So let's do the reverse then. Let u be equal to tangent inverse, also known as arctangent of x, and dv be equal to x squared. Okay, so what is the derivative of arctangent? 1 over 1 plus x squared, right? Because think going backwards, the integral of this is arctangent, right? So the derivative of arctangent is 1 over 1 plus x squared. Okay, what about antiderivative of x squared? That's x cubed over 3. So using the formula, integration by parts formula, uv minus integral of v du. We're going to multiply these two together. U times v will be x to the 3 over 3 times arctangent of x. And you can use either notation as far as I'm concerned, tangent inverse notation or arctangent notation, minus the integral of v du. Now we want to multiply those within the integral sign. And then there I'm going to pull the 1/3 out. So I have here x cubed times 1 over 1 plus x squared. And I'm going to write it like this, x cubed over 1 plus x squared dx. Okay, you might say, wait a minute, here we have an integral. We don't know how to integrate this. Are we stuck here? The integral of x cubed over 1 plus x squared. But we have seen things where degree of the top is higher than degree of the bottom, right? We have seen a method to tackle that. So let's see if that method works in this case as well. So I'm going to do a long division of x cubed divided by 1 plus x squared. I'm going to put it like this, x squared plus 1. So the question is, x squared goes into x cubed how many times? X times, right? So then x times x squared is x cubed, x times 1 is x. Now we're going to subtract. So these cancel, and you have minus x. So it looks like this quantity is equal to the quotient, which is x, minus remainder over divisor, which is x over x squared plus 1. So let me rewrite that quantity in its simpler form. So don't forget to carry the first term all the way with you to the last step. Minus 1 over 3 times. Okay, so this is where, don't forget the integral sign. We have divided those polynomials, and we got the quotient minus remainder over the divisor. 1 plus x squared or x squared plus 1, same thing. With a dx on the outside of everything there. Okay, you can see that there's a dx at the end. Okay, so now once again, let's keep the first term as it is. And keep the 1/3 on the outside. Now to integrate, the integral of x is x squared over 2. And the integral of x over 1 plus x squared. Okay, so right there, x over 1 plus x squared, what do you think you have to do to integrate that? Hopefully everybody knows that really well by now, right? Use substitution, let u be 1 plus x squared, and you're going to end up having like 2x dx equals du. So x dx is du over 2. And this is going to become just like 1 over 2 du over u, right? Which function would be needed to integrate that? If you said natural log function, you're absolutely correct. So the way to integrate that will be 1 over 2 times natural log of 1 plus x squared. And plus c on the outside of everything. And the last thing I'm going to do is clean this up just a little bit. So x cubed over 3 arctangent of x minus x squared over 6. I'm distributing this times that, and then don't forget this times that will be plus 1 over 6 times ln of quantity x squared plus 1 or 1 plus x squared. And you can't keep the absolute value or drop it, just use parentheses because x squared plus 1 is always positive anyway. So either one of those should work. Okay, so we looked at a few unusual cases, and I saved the best to the last. There's one example that is very, very unusual. I call those the circular problems, and we're going to look at one of those in the last segment on integration by parts.